Problem number 23. I guess what we should do is talk a little bit about logistical equations. So what we've been talking about are exponential equations. Now exponential equations are what we use to model growth. So an exponential equation looks like this, right? So this is an exponential. Right? And it looks like y equals, or sometimes we list it as f of x equals a times b raised to the x. And if I were to graph it, it usually kind of looks like this, right? And what happens is this is like a doubling or tripling effect. We use it for growth models because Mr. and Mrs. Adams were two people. So if you were to count the Adams family tree from Mr. Adams and Mrs. Adams, right? There's two of us, right? And then we have 4 children. So we doubled, right? And then someday my children will have children. If each one of my children has 4 children, holy moly, that's a lot of kids. But that is population growth, right? And so it's like a doubling effect. And the same occurs with bacteria. There's kind of like this doubling effect or a tripling effect. And so any type of population growth is going to be exponential. Now in the real world though, let's think about bacteria. If I take bacteria and I put it in a petri dish, and the bacteria doubles, and it doubles, and it doubles, and it doubles, and it doubles, at some point in time, the bacteria can no longer be sustained in the petri dish because either they'll run out of food or the sources they need to sustain life, or the dish can only hold so many bacteria. So a better model for population growth, or actually to model population, is what we call the logistic function. And so a logistic function is very similar. So we say y, or sometimes if we use function notation, y is equal to c all over 1 plus a times b raised to the x. That's the standard form. And here's what it looks like. So same thing, we start in the petri dish, and we have, I think we did an example where we had 100 bacteria, and then it doubles every 20 days, right? Well, it doubles and it doubles and it doubles. That's the exponential part. But then the dish can only hold so many bacteria. So it has a limit to growth. So it'll grow up until a point, and then this is what we call the limit to growth. And it's kind of, you can think of it like a vertical asymptote. So no matter what happens to those bacteria, once that petri dish is full, it can only hold so many bacteria. And so they'll still produce more bacteria, but some of the bacteria will be forced out of the dish or they won't live anymore, but something's going to happen. And so the equation that we use to model this behavior is this. Now there's a couple of things I want to tell you. C represents this limit to growth. Okay? And that's pretty much it. And then the other thing is, this right here, whatever x is, x equals 0, that's our starting point, the initial value. And so Mr. Adams, just to be, I'm supposed to write out the whole word initial value, but I'm just going to put ID. Okay? So the initial value occurs when time is at 0. Now I could start time anywhere, right? I could start 0 now. Or now. Or now. Alright? So whenever I start counting my time, that's the 0, that's the initial value. Graphically, it should be the y-intercept. And that occurs when our variable x is equal to 0. Does that make sense to you guys? Yeah. Alright, so let's do problem number 23. Before we do problem number 23, are we good on that? Do you understand what I'm saying? Are there any questions? Okay, so now let's look at problem number 23. Now problem number 23, can I erase this or move on? You guys have this written down, right? Yeah. All right. So if I move on to the next slide, problem number 23 gives us some conditions of some growth. Well, it says that the initial value of this population was starting at 10. I don't know what it is. The book doesn't tell me. There was 10 of something. Okay? And that 10 of something was able to grow up to 40. That's a G, not a 6. Okay? So the limit to growth is 40. And then they tell me one other thing. It passes through the point 1 comma 20. So we have something. It starts with 10 of whatever that something is. It has a limited growth, which means that we're going to have to find, I mean, your textbook tells you to find the logistic model. But that's what we're going to have to do, because the logistic model involves something that grows, but then is limited in growth. And then to kind of give us a clue, they told us that it passes through the point 1 comma 20. Okay? Now, one other thing I want to remind you, it passes through that point, but remember, it also passes through 0 comma 10 because that's the initial value, right? So we have 2 points. Now, on your calculator, I'm going to say on your calculator, which means I should hear everybody's covers of their calculators coming off and being turned on, right? Because you want to learn how to do this too on your calculator. I'm going to hit edit. Well, bam, with the bacon sizzle, I got 0, 10, 120, and then because we said that the limited growth, it kind of looks like this, right? My graph, if I graph this, it's going to look like this. We know it's going to look like that. Where this is 40, because that's the limit to growth, so it's going to have like a horizontal asymptote of 40. We know that the initial point starts here, which is going to be 0 comma 10, the initial value. And hey, you know what? It's going to cross through 1 comma 20. Now we're going to use a bunch of algebra to find an equation of the line to fit that one formula, f of x equals c over 1 plus a times b raised to the x. But when we're done, we want to make sure that we have the right answer. So what I'm going to do is I'm going to pick a point way over here. And we know that once we get way over there, in other words, as x approaches infinity, what will my y value approach? 40. So I'm just going to make up a number. And what I did is in my list, I put 100 equals 39.99. Okay? You guys with me so far? If you guys can't see the screen, I can do something like that. Is that better?
Yeah.
All right, we'll do that. So that's what I have. And then what I'm going to do is I'm going to, does everybody have these points plugged in? All right, so now what I'm going to do is I'm going to turn my plots on. Oh, hey, it's already on. But I'm going to hit zoom, and I'm going to do stat plot, right? So remember, stat plot will fit the window to fit all those points in, which is option number 9. And so there are my 3 points. Now, we're going to do some algebra in a second. We're going to get an equation, and I'm going to plug the equation, and if my equation is correct, what will it do? Yeah, the curve should go through all 3 points. Hopefully. All right. Anybody have any questions at this point? All right. So now that we've done that, let's keep going. All right, so you guys may not remember this because I just taught it to you. It's the first time you saw it about 2 minutes ago. But we said that a logistic model is f of x is equal to c over 1 plus a times b raised to the x, right? We also said that c was the initial value, or no, c was the limit to growth, which was 40, right? Is that true?
Yeah.
All right. So I'm gonna write out each step. So that means that f of x should be 40 over 1 plus a times b raised to the x, right? Now, you know what would be awesome is if I knew what a and b were. That would be amazing.
You just solve for it.
Yeah, we're going to get to that. We're going to solve for it, and I think you already kind of know what a would be. So let's look and see. We said, no, a isn't the initial value, but we use the initial value. So what is the initial value? This is like x comma y, right? All right, watch this. If this is y, what was y? 10 should equal 40 over 1 plus a times b. What was x? 0. Oh wait, we don't know what b is, Mr. Adams. How are we going to do this? I don't know. Oh wait, what's b to the 0?
1.
1. So what's 1 times a?
A.
So this should be 40 over 1 plus a, right? Is that right? Okay, so what do I plug in for a to get 10? Because remember, all this stuff equals 10.
40 divided by 10 is 4, then you have 1 plus a equals 4.
Right, so yeah, so let's just do it algebraically so you see it, okay? You're right. So I'm going to say 10 is equal to 40 all over 1 plus a. We're going to cross multiply because this is like 10 over 1, right? So I'm going to say 10 times 1 plus a is equal to 40. She said all these steps out loud. I'm just writing it down so that way for some of you visual learners. So then we divide 40 by 10, right? And then we get 1 plus a is equal to 4, or a equals 3. Is that right? Yeah. Okay. So we found C, we found A. What do we need next? B. So let's plug in and see what we have. Right now, as it stands, we have f of x is equal to 40 over 1 plus 3 times b raised to the x, right? I could probably solve this. Oh, instead of f of x, can't we think of f of x as something like this? I could probably solve this equation if I had a point that was on the line. Wait a minute. The book, for some weird reason, gave us a point that was on the curve. 1 comma 20. It's as if they wrote the book to teach us. All right, so here we go. So we said the point 1 comma 20 is on the line. That's like an x value and a y value, right? So if I put a 20 here, equals 40. And then 1 plus 3 times b raised to the, is that 1?
Yeah.
All right. Well, if we cross multiply, I think of that as like 20 over 1. I get 20 times the quantity 1 plus 3 times b to the 1. What's b to the 1? B to the 1 is b. 3b. Well, because I got to follow order of operations. So if b was a number and I knew what that number was, what would I do first? I'd have to multiply first. I couldn't add 1 and 3 and then multiply. If I say 4b, I'm adding the 1 and 3 first and then multiplying by b. And that's not what we're doing, right? Plus, they're not like terms. You can't add 3b with 1. What do you mean they look like one term?
Never mind.
They're not, right?
Yeah.
They're not like terms, okay? But that's okay. So anyways, it equals 40. Divide both sides by 20. I've got 1 plus 3b is equal to 2, right? 3b, if I minus 1 from both sides, is 1. B is equal to 1 over 3. We found A, B, and C. Can we write the equation now?
Yes.
Not exactly. I have to have a sip of my coffee. All right. So my equation, which was originally f of x is equal to c over 1 plus a times b raised to the x, and we said that c was the limit to growth, which is 40. We said that a was some complicated calculation, but remember that it's evaluated. We could calculate a by using the initial value, right? Because when x equals 0, b kind of goes away. That's convenient, isn't it? So a is equal to, based on the initial value, we said that was 3. And we said b was equal to 1/3. So what does that mean? Okay, now be careful with this. We're going to say f of x is equal to 40 all over 1 plus 3 times 1/3 raised to the x. Some of you will be tempted to multiply 3 by 1/3. We cannot. How come?
1/3 is 3x, but 3 is not.
It's an exponent, and so exponents come before multiplication, so we can't multiply before we do the exponent, right? Any questions?